And we had these various guidelines for minimum mass design depending upon the shape, whether it was a tri rod, whether it was a different cross section, or whether it was a thin sheet. So in the last class, we had looked at the fact that if, depending upon the constraints and their magnitude, you had a line with a slope of 1.5 that was placed over here related to this material index, without taking into account shape factors, the materials below this particular line would all be eliminated. Those above this line would be under consideration. Then we indicated that for a steel, for instance, one of the types of materials should be largely eliminated. If you go from a shape with a phi of 1 to a shape with a phi of 10, you could basically get a strength value that was now modified based on the material index. So, do you remember? It would be sigma f divided by phi square. So instead of 7.8, it would be about 0.078, which will be roughly over here in density. And instead of about 120 megapascals in strength, you would come down to about 1 megapascal in strength. So we had a way in which material substitution at constant strength allows for differences in shape. And we said now that the modified material index, as we saw the derivation, is given by this term over here, which includes a shape factor. And so you end up obtaining a new material whose modified strength is sigma divided by phi square and modified density is rho divided by phi square. And basically we begin to access this part of the space just by changing the combination of shapes for various materials. And so you can basically effectively expand the materials window to obtain new materials. The second scenario that we considered in the last class was bending stiffness, so stiffness limited designs. And so we had the area moment I, which was given by a square by 12 for this square cross section. If you went to any new shape while keeping the area constant, you could then define the shape factor as the ratio of the stiffness for the new design normalized to the stiffness of the square cross-section beam. And this would basically come down for a constant material to be the ratio of the area moments. If you substitute the value for the original area moment I for the square cross-section beam as a square divided by 12, you get shape factor for any new shape to be 12i divided by a square. Knowing I and a, you can calculate a shape factor for each different design. So if you had stiffness limited designs, we saw that a material index could be generated where you could modify the material index by including a phi term next to the modulus term and under the square root. So this would be the case for a beam of length L loaded in bending and must support a specific stiffness without failing, be as light as possible. So the objective function is to minimize the mass of the beam per unit length. And so you can select the material and shape based on maximizing this quantity over here, which is a modified material index that includes shape. So our job would be to derive an equation. So we are looking at the stiffness of the beam S that's loaded by a force F and a span length of L. So the derivation goes as follows. You know that the function is the beam. You know the objective is to minimize the mass, where mass is A times L times rho. And the constraint is the stiffness, which is some constant C, which depends upon the geometry, times EI divided by L cubed. And the appendix that we saw gives a whole number of values for C and I. E depends on the material and L cubed is a geometric constraint. So how do we bring the shape factor in like we did for the strength limited design? So in order to do that, what we have to do is look at the fact that for a stiffness limited design, the shape factor is the ratio of the area moment divided by the area moment for the reference square cross-section material, which is 12I divided by A square. So now if you rearrange terms over here for I to use in this equation, I would be phi times A square divided by 12, and A from the first equation can be obtained as m divided by L times rho. So if you insert the value of A into this equation over here and then go ahead and introduce I into this equation and rearrange terms, what do you get? You basically get a very familiar term that we had derived for stiffness limited designs, where we did not take into account the shape. And it is only the material index is one where you can minimize mass by maximizing e to the power half divided by rho. So now you just have a modified material index as we had indicated, where you have phi times e to the power, the whole to the power half divided by rho. So materials with the largest value of this particular material index, which is modified with the shape factor, will give you a combination of material and shape which has the minimum mass. So the shape factor is part of the material index.